Welcome. Today, we are diving into how to design effective specifications. As we've discussed before, our work in applications development is always guided by the big three goals: making software safe from bugs, easy to understand, and ready for change. A well-designed specification is the primary tool for achieving these, ensuring that our code is correct today and stays correct in an unknown future while communicating clearly with other programmers. By the end of this session, you should be able to identify and assess undetermined versus deterministic specs. We'll also distinguish between declarative and operational styles and learn how to compare the strength of different specifications. Finally, you'll be equipped to write coherent specs that strike the right balance of strength for your specific project. When we evaluate a specification, we look at three primary axes. 1. Determinism. Does the spec permit only one possible output or a set of legal outputs? 2. Declarative versus operational. Does the spec describe what the output is, or does it give a recipe of how to calculate it? 3. Strength. How large is the set of legal implementations that satisfy the spec? A specification is deterministic if, given an input that satisfies the precondition, the output is completely fixed. For example, consider a function, find exactly 1. Its precondition is that the value occurs exactly once in the array. Because of this strict requirement, there is only one possible valid index to return. There is no ambiguity. The return value is completely determined. In contrast, an undetermined specification permits multiple legal outputs for the same input. Take the find one or more example. If the precondition is just that the value occurs at least once, and the effect is simply to return an index where the value is found, the spec is undetermined. If the value appears 3 times, returning any of those 3 indices is considered a correct implementation. It is important for CS majors to distinguish undeterminism for non-determinism. Non-deterministic code behaves differently each time it runs. Think of a random number generator or race conditions in concurrency. However, an undetermined specification can satisfy by a perfectly deterministic implementation. The implementer makes a choice at the time they write the code, like always, searching from the beginning. And that choice remains fixed even though the spec allowed other options. An operational specification provides a series of steps, essentially like pseudocode. A declarative specification, which is almost preferable, instead describes the properties of the final outcome and its relationship to the initial state. Think of it as defining the what rather than the how. Declarative specs are usually shorter and easier to understand. More importantly, they are implementation independent. By not detailing the intermediate steps, you avoid inadvertently exposing the implementation details that a client might rely on. This gives the implementer the freedom to change the algorithm later without breaking the client's code. Programmers often fall into the trap of writing operational specs because they want to explain their code to a maintainer. However, those details belong in the body of the function, not the specification. For instance, a spec saying a function goes down the array suggests a specific search order that might not have been intended, potentially trapping the implementer into a less efficient algorithm. We say spec S2 is stronger than S1 if the set of the implementations that satisfy S2 is a strict subset of those that satisfy S1. If you imagine a Venn diagram of all possible functions, a stronger spec defines a smaller, more constrained region. It makes more promises to the client and places fewer demands on them. To determine if S2 is stronger than or equal to S1, we follow two logical rules. Either S2's precondition is weaker than or equal to S1's, meaning it accepts more inputs, or S2's postcondition is stronger than or equal to S1's for the states that satisfy S1's precondition, meaning it allows fewer outputs. Think of this as a logical contract. You are offering the client more while asking for less. If S2 is stronger than S1, then any implementation that satisfies S2 automatically satisfies S1. This means it is safe to replace an old spec with a stronger one. Clients won't be upset because their existing inputs are still valid, and the guarantees they rely on are still being met. Let's look at an example of strengthening a spec by weakening its precondition. S1 requires the value to occur exactly once. S2 requires the value to occur at least once. S2 is stronger because it handles all the cases S1 handled, plus many more. It places fewer restrictions on the client's input data. Now let's look at strengthening the postcondition. S2 says, return any index I such that array index equals value. S3 says, return the lowest index I such that array I equals value. S3 is stronger because it constrains the output more tightly. It makes a specific promise about which index is returned, whereas S2 left that up to the implementer. Not all specs can be ranked by strength. Some are incomparable. This happens when one spec has a weaker precondition, but the other has a stronger postcondition. For example, a spec that requires nothing but returns any index cannot be strictly compared to a spec that requires a value to exist but returns the lowest index. Neither set of legal implementations is a subset of the other. To visualize how specifications work, imagine a vast space containing every possible TypeScript function implementation. Each individual point in this space represents a specific piece of code, such as the find first or find last implementations we discussed earlier. A specification acts as a boundary, defining a specific region within this space. If a function's behavior satisfies the precondition implies postcondition contract, it sits inside that region. If it doesn't fit, it's outside. The spec serves as a firewall. For clients, it doesn't matter which specific point or implementation they are using, as long as it's within the specified region. Stronger specs define smaller regions because they are more constrained. There are fewer legal ways to satisfy the strict requirements. Weaker specifications define larger regions, offering the implementer more freedom to change the algorithm, optimize performance, or fix bugs without stepping outside the boundary and breaking the client's code. We now turn to a major design choice: mutability. While mutable types like array might seem more powerful than their immutable counterparts, like read-only array, they often undermine our big three goals. Mutability makes code harder to understand and makes contracts difficult to enforce. The primary danger here is aliasing, when multiple variables references point to the exact same mutable object in memory. Consider a diagram of a function, sum absolute array, which is designed to sum the absolute values of numbers in an array. To be efficient and avoid creating a new array, an implementer might mutate the input array directly using the math.absolute function in a computer's memory. The variable myData in the main program and parameter array inside the function are aliases, two names for the same bucket of data. If the function changes the data to save memory, the caller's original data is destroyed without them realizing it, leading to latent bugs that are incredibly hard to track down. Now imagine a function, start of spring, that calculates a date. To improve on performance, the implementer might cache the results, meaning they save the date object in a variable called groundhog answer and return that same object every time the function is called. If a client receives this date and decides to move their party date 1 month later by calling setMonth, they aren't just changing their local copy because date is mutable. They are actually changing the cached value inside the function itself. Every future call of start of spring will now receive the wrong modified date. To avoid the risks of mutable returns, an implementer can use defensive copying. Instead of returning the original cached object, the function returns new date groundhog answer, creating a fresh copy for every client. While this protects the internal state, it is inefficient because it wastes time and memory creating copies that 99% of clients might never even change. The superior solution is using immutable types, which can be safely shared across the entire program without any risk of one part stomping on another's data. When we use mutable objects, we end up with lifetime contracts. If a spec says, caller may never modify the return date, that is a burden the client must remember for the entire duration of the program. It's a bad design because it's hard to verify and reduces the freedom of both the client and the implementer to change their code independently. Using an immutable type makes these bugs impossible by design, as the compiler simply won't let you change the value. Typescript provides interfaces like read-only array, read-only set, and read-only map to help. If you declare a variable as a read-only array, the compiler will give you a static error if you try to use mutating objects like push. Even though the static type, what the compiler sees, is read-only array, the dynamic type, the actual object in memory, is still a regular mutable array. The read-only part is just a restricted view of that mutable object. It is vital to understand that a read-only array is not guaranteed to be immutable. If you create a regular array and then assign it to a read-only array variable, you have created an alias. If another part of the program still has a reference to the original mutable array, they can change the data under your feet, and your read-only array will change too. Only true immutable types like string, number, and boolean are completely safe from this aliasing risk. When designing specifications, they should be coherent, meaning the function performs exactly one complete task. Signs of trouble mean long argument lists, Boolean flags that switch behavior on or off, or names like does X and Y and sometimes W. For example, a function that both counts long words and finds the longest word should be split into two separate simple functions to be easy to understand and ready for change. A good spec strikes a balance in strength. It's strong enough. It must give the client a useful guarantee. Avoid operational specs that leave the state of the program undefined or messy if an error occurs. Weak enough. Don't promise the impossible. For example, a function to open a file cannot guarantee success because the file system might lack permissions or the file might not exist. It should instead promise to attempt to open the file. The choice to use a precondition is often an engineering trade-off. Preconditions are usually used when checking a condition would be too expensive. One example would be for a binary search function, requiring the array to be sorted as a precondition is necessary. If the function had to check if the array was sorted every time it ran, it would lose the performance benefits of the binary search. However, whenever possible, it is better to fail fast by throwing an exception as a postcondition if the arguments are invalid. How you design a spec depends on the scope of the function. Helper functions. If a function is private and only used by you within one module, a precondition is fine because you control every single place that the function is called. Public library functions. If the function is exported for others to use, you shouldn't rely on preconditions. Instead, you should specify that function throws an exception for bad inputs, helping the caller identify their own bugs quickly. Specifications exist on a spectrum of visibility. Helper functions. One client, one implementation, one programmer. Exported functions. Many clients within one program used by a team. Library functions. Used by many programs, often by developers around the world, like an npm package. Standards. Many different implementations, like Chrome, Node, and Safari, all following the same specification, like the ECMAScript standard. In summary, well-designed specifications are the foundation of professional software construction. It is safe from bugs, easy to understand, and ready for change. A specification is a firewall that enables separate development. It allows the implementer to improve their code and the client to change how they use it, as long as they both respect the contract. Declarative is almost always better than operational, and immutability is your best defense against the complex, dangerous bugs caused by aliasing and mutable objects.